terminate, it's not clear whether this will eventually stop. But this will eventually produce a classifier which correctly classifies every data point. But even assuming that it terminates, will it then correctly classify every data point? What do you think? If it ends at some point? So remember that it ends if you can't find a data point that satisfies this condition. So that means that if it ends, then yi times this inner product is going to be larger than 1 for every data point. So what can we say about the classifier if that condition holds?
Are we assuming that this meets the conditions, like that there's literally separable data?
Oh, yes, yeah, good point. So this is, so I said this, but I didn't write it down. So that we're assuming here that the data is linearly separable. So what I wrote down here is, this is a stronger condition, that there exists W such that the inner product is even larger than 1. So this means that's linearly separable. So yeah, if the algorithm does terminate, then we have something such that this inner product is always larger than 1. That means that every data point gets classified correctly. So really the question is, does the perceptron algorithm ever terminate? Does it ever result in does it ever end up in a state where there exists no more data points which are incorrectly classified? And this is something that we want to show. And I think the proof is kind of neat. There's like a clever trick that you can use. So the idea is basically as follows. So there are 2 quantities that we can track as the perceptron algorithm evolves. So you can define these 2 quantities. So let's suppose, I'm going to write W star. So suppose W star correctly classifies everything. W star correctly classifies the data set. So we assume the product of W star xi times yi is greater than or equal to 1. So correctly classifies the data set with some room to spare. And we want to use this to measure how well is the algorithm doing. And one way to measure how well the algorithm is doing is to see whether the W that we get from the algorithm, whether it's getting closer to W star, right? So, like motivated by that, we can say that we can define this quantity, like let's say f of t, we can define it to be the inner product between W star and W time t. So we want f to be increasing, right? Because W star is good. If WT gets closer and closer to W star, this quantity increases and we're happy. Now that's one thing that we can measure. You can also measure another thing. We can measure how much the norm of the vector that we're getting is increasing. So we can look at G of t is equal to, let's define that as the norm of WT. And this might be like an arbitrary thing to measure right now, but you can see through the proof that by tracking both of these quantities, that one of them is going to increase faster than the other. And if one of them increases too much faster than the other, then we can get a contradiction, and that's what we're going to show. So I guess to begin with, does anyone see like any way that we could relate f of t to g of t? Like, is there a way we can bound one thing in terms of the other?
Cauchy-Schwarz.
Yes, you can use Cauchy-Schwarz. So what does Cauchy-Schwarz say? So we can look at, so we have f of t, and that is equal to this. And Cauchy-Schwarz says that this inner product is less than or equal to the inner product, the norm of WT, and the norm of W star. WT, that's equal to GOT, so that's equal to norm of W star times GOT. So we can bound F of T above by GOT. Now, if we could show that GOT increases a lot slower than F of T, then eventually this algorithm has to stop, right? Like, let's just make up some numbers. Let's suppose that like GOT is equal to like C1 times T cubed, and F of T is equal to like C2 times T to the 4. If we knew this, then after some amount of time, the algorithm would have to stop because T to the 4 grows faster than T cubed, so eventually this is, you're going to get a contradiction from this. And that's what we're going to do with different numbers. Okay, so let's track how this changes over time. So let's look at F of T first. So whenever you have like a quantity that you're tracking as like an algorithm evolves, what you want to do is you want to relate how this F of T plus 1 to F of T. So that's what we're going to do. So we can write down F of T plus 1 that's equal to inner product of WT plus 1 with W star. And we use our expression the way we define WT recursively. So we can write this as the inner product of WT plus YI XI, inner product of this with W star. And now you see we can relate this F of T because we can split this up. And you see here, this is, by definition, this is equal to F of T. And the second part, is there anything you can say about that? Yeah, so by assumption, since W star correctly classifies the data, we can say that this is greater than or equal to 1, so we can say this is greater than or equal to F of T plus 1. So what does this tell us? This tells us, okay, at each step of the perceptron algorithm, F of T is increasing by at least 1. So that means that F of T is growing at least at a linear rate. So that means, like, we can write down by induction, we can write down F of T is greater than or equal to F of 0 plus T. And okay, so we can look at what happens at time t equals 0. So at time t equals 0, we start at W0 is equal to 0. So that means F of 0 has to be equal to inner product of 0 with W star. So it always starts at 0. So we can write it in this way. Simplify even more and write it down as F of T is greater than or equal to T. And now we can do a similar analysis for GOT. So we can write down GOT plus 1 is equal to WT plus 1. This is equal to WT plus YIXI. Now, thinking about the norms of things can be complicated, so let's just square everything so that we can write this in terms of dot products. So we can write down WT plus 1 squared is equal to WT plus YI xi. Okay. So let's do the only thing we can do here and expand this out. We can write it out as so first the norm squared of WT, and then we take the cross terms, which are given by 2yi product of WT with xi, and then finally we have norm of xi. I canceled out the yi's here because you know that the yi's are either 1 or minus 1, so the yi squared is always equal to 1. Okay, so we see this thing here. This is, by definition, that's just g of t squared, so we can write this as g of t squared plus, well, this is the norm of the xi squared, and finally we have here, this is, well, let's just write the same thing for now. So we can bound this as g of t squared. So here we need a bound for the norm of the data point. So let's just assume here. Let's assume that the xi squared is like at most unit length. So let's just say that it's g of t squared plus 1 plus some other stuff. So, sorry, anyone have a question? Yeah, so you could do this for like any finite value. You could assume that the xi squareds are like less than 10 or something, and then everything will just be like multiplied by that amount. I'm just using one here, just to make it concrete and to keep it simple. And we also want to bound this thing above by something. The 2yi times
Well, from above, that's less than 1.
above that's less than 1.
Because xi yi is a point such that yi times the other bucket wt xi is less than 1.
Oh yeah, good point. Yeah. So this is where we use that the xi is not correctly classified. So we know that the perceptron algorithm will only select the point if this inner product is less than 1. So we know that this thing is less than 2. Okay, so this is g of t plus 1 is less than or equal to g of t squared plus 3. Okay, and we can do a similar thing. So we know that g of 0 is also equal to 0 since we start at the 0 vector. So that gives us g of t squared has to be less than or equal to 3t. So that gives us g of t is less than or equal to square root of 3t. Okay. Now we finally we can use this inequality we got right at the beginning. So we know that g of t is less than or equal to g of t grows like square root of t, while f of t grows like t. So that means f of t is growing faster than g of t, but we have this inequality in the opposite direction here. So what does this tell us? This tells us we can combine everything. We can write down t is less than or equal to okay, so t is less than or equal to f of t, which is less than or equal to norm of w star times g of t, and this is less than or equal to form of w star times square root of 3t. And then now we can combine the terms of t, so we get that square root of t over 3 has to be less than or equal to w star. That means t is less than or equal to 3 times form of w star squared. Okay, so what this tells us is that the algorithm, if we run for any number of iterations t, that t has to be at most this quantity. So that means it has to stop after this number of iterations. And so we're done. So that's the perceptron algorithm for this case. Any questions on this?
Did we answer, does it correctly classify her point? We answered terminated, right?
Yeah, so the answer is the algorithm terminates. And so then the question is, does it correctly classify every point? Well, so we know that the algorithm will only select a point if it's not correctly classified yet. So if that inner product is less than 1. But if we know the inner product is greater than 1 for every single data point, then that means every data point is correctly classified. So terminates means that everything is correct. Any other questions?
I was a bit late, so I might have missed this. Why is it that we're checking the inner product compared to 1 instead of 0?
The inner product compared to 1 instead of 0. Oh, that's a great question. So, so the reason is that we want to, so doing the inner product there's less than 1 versus less than 0, it gives you some margin of error that like you can allow every data point to be like every data point which is correctly classified is also correct by a wide enough margin that it helps you here.
Okay.
So if we only know that it's greater than 0, then if you're just talking about it in terms of the proof, if we only knew that it was greater than 0, then here you would get here you wouldn't get the 2, you would just get this as.
I think you ran into issue in the f of t case.
Yeah, it might be the f plus t, right?
But so for making this assumption, we're going to need, for it to terminate, we're going to need our data to not just be linearly separable, but like by a non-negligible margin as well.
Yeah, I think in order to make the proof work, you need to have it with
I guess because if the margin was essentially 0, you'd end up with your norm of w star kind of exploding.
Yeah. If you could do it. It doesn't have to be specifically 1. You could have any margin that you want. Mm-hmm. But like as you get closer to 0, the number of steps that you need will like blow up.
Okay. Thank you.
Any other questions? Okay, so then we can move on. I also wanted to talk about a variant of, like some variants of this perceptron algorithm, because, so this specifically is for like a linear model, but you can also use it for other types of models. So you might recognize the steps taken by the perceptron algorithm. It might remind you of like a gradient type, like some sort of gradient descent. And you can actually think of this as a type of gradient descent. So let me just like describe what I mean by gradient descent here. So by gradient descent, we mean that we have like some sort of loss function. Let's say we have a loss function L. And so we have a loss function L, and if we have a data point xi and we predict we predict yi, then we might have like a loss associated with that. But I guess more let's just say that we have a loss function L of theta, and we want to perform like we want to optimize in theta such that it minimizes L. So the way we define gradient descent here is, so let's say theta at time t plus 1 is equal to theta at time t minus theta times gradient of L of theta t. Another question is, how do we think of this perceptron algorithm as a specific case of of gradient descent? So we want to say here, so in this case, theta is equal to W, and so if we do WT plus 1 is equal to WT plus that quantity plus YIXi. So I guess here you could think of, so here we want like eta equal 1. So what does this mean? It means that like gradient of W should look something like minus y times x if we classify the point incorrectly. And it turns out here, like we can use a loss function that's called the hinge loss. So let's just define it. So the hinge loss, this is given by, say, L of y with y hat. So here y hat is the predicted y value and y is the actual y value. And we define it in the following way. So we define it to equal 0 if y times y hat is larger than or equal to 1. So we correctly classify the data point with some margin 1, then we say the loss is equal to 0. Otherwise, we want to say that we have some amount of error, and the amount of error increases the, like, if y times y hat is really negative, then we did a really bad job of classifying the data point. So in that case, we want it to increase, so we can write, so let's define it this way. So let's say 1 minus y hat if y hat is less than 1. So like it makes sense to have it like scale negatively with y hat, right? Like if y times y hat is really negative, then we should get a lot of error, so we take minus of that to get something that's really big. The reason we use the 1 here is just so that we can make the loss function continuous. Because if y hat is equal to 1, we want these two things to agree at the breaking point, so we have that 1 there. This is how we define the hinge loss. Now let's just check that the hinge loss is giving this gradient update. So how do we get this from this? So we can write down. So let's write down loss of. To be specific, we should write down the loss for a specific data. So let's say that the loss of W with point xi and yi, so this is equal to the loss of, well, the actual value is y, so let's write down yi here, and we compare it against the predicted value, and the predicted value is, in this case, equal to W with xi. Okay, so that's how we define this, and we want to compute the gradient. So let's compute the gradient of this with respect to W. So gradient of that function, so we can write that down as, we can split into cases where the, you get that it's correctly classified and where it's incorrectly classified. So, well, down, so this is equal to gradient with respect to W of L of WI. And then we can use the chain rule here. So in the case where it's correctly classified, you get 0 if it's correctly classified with margin. It's greater than 1. And if it's not correctly classified with margin, then we take that part and we get, okay, so the first part is we take the derivative of this with respect to the y hat, so we get, this is minus y times something, and for the something, then we take the derivative of this with respect to w, so we take this as minus yi times xi. Okay, so we see from this that this is, the step that we're taking with the perceptron algorithm is exactly like a gradient step. Because then if we write this down, then we get w of t plus 1 is equal to w of t minus 1 times the gradient. So then this just becomes plus yi times xi. Right? Because here we're only using data points which are incorrectly classified. So we can see from this that the perceptron algorithm is exactly gradient descent for a linear classifier when we use the hinge loss. So that's like a, I guess, a framework for that includes the perceptron algorithm as like one example. So that might suggest, okay, then you could also do the perceptron algorithm with different step sizes. So instead of yi times xi, you do like eta times y times xi, where eta is some smaller step size. So you could also consider different cases of this, and you can use the same proof to show that you'll converge to a classifier that correctly classifies the data point for any choice of step size here.
Should the loss be averaged over all the i's? Because
Yeah.
we just like chose some I, right? But it shouldn't be fixed.
Yeah. So if you want to compute the empirical loss, then yeah, you would write it down as, so maybe you could write down like R as the empirical loss of W summation, like the average of all these losses. But you could also consider the loss for individual data points. Another interesting point is that, so this is, well, I said this was an example of gradient descent, but maybe more specifically, it's kind of like a stochastic gradient descent. So you don't do a gradient with respect to this like full population loss. You just choose a single data point at each step and update with respect to that. And this is kind of interesting because it doesn't actually matter which point you choose at each step, as long as it's the point that was incorrectly chosen. And that's not, like, in these proofs, usually it depends a lot on which exact points that you choose. So you could think of this as a stochastic gradient descent. So at each step you choose some point randomly that wasn't correctly classified. But then there's no like randomness in this proof. You just are going to converge after some set number of iterations, no like expectations or anything. So it's different from the way that most like stochastic algorithms work in that sense. Anyone have any other questions on this? Let's see, how much more time do I have? Like 10 more minutes? Okay, so I also wanted to say, like, okay, so this is like an example of gradient descent, like a gradient descent algorithm. That might suggest, okay, so can you move beyond like linear models? Like, can you do gradient descent with the hinge loss for different types of models and get like a similar convergence analysis to the And the answer is actually yes. So, I can so interestingly, like, you can also do this for neural networks with the Higgs law. So, let me just very quickly describe what I mean by a neural network. So the model that we were looking at before was a linear model. So f of w x, you have a model that's parameterized by w, and you have a data point x, and that will give you this inner product of w x. Right, so it's a linear model. And you can also do this more generally. You could use any model that you want. It doesn't have to be linear. You could use a neural network. So what I mean by neural network here is like a two-layer neural network. So you have a matrix W. So we write down f of wx is equal to so what we do is we apply W to x, so you take a matrix, you apply it to x, then you apply some function sigma, which I will say in a minute, and then finally you take an inner product of that with some fixed vector W. And so by sigma here, so sigma is equal to ReLU of x, which is equal to the max of x with 0. So the reason why we include this sigma here is as a nonlinearity, because if you only do v transpose times wx, then it's a linear model in the back of here. So we include ReLU to add some nonlinearity to the model. So you have this nonlinear model, and you can also say the perceptron algorithm for this. Actually, here I said ReLU, but you could also do leaky ReLU. So you could do and that gives you max of alpha x with 0, where alpha is between 0 and 1. So this is another type of model that you could consider and do this gradient based algorithm for. And you can also show that gradient descent converges to a zero loss solution for this, which is surprising because usually for neural networks it's hard to prove convergence. And maybe let me just briefly sketch out how you do this. So we can write down the same thing for f of t and g of t. Let me just assume here like that w is just a single vector. So we have v transpose and sigma. Let's just say that you have you have something like this. So like maybe 2 neurons. So we have sigma w1 times x minus sigma w2 transpose x. And like the idea behind the convergence proof in this case is like you can write down f of t plus 1 by the same thing up here. This is equal to f of t plus, in this case, instead of having, so we look at the yi times inner product of xi with w star, then that basically ends up being, if you write out the gradient computation here, it becomes like plus beta times yi inner product of xi with w star. And here beta is either equal to like alpha or it's equal to 1. So you can basically sketch out the same proof for the linear model for a leaky ReLU network, except in some places where you write 1, you get a different slope alpha, where alpha is your slope of your ReLU. So you can get a proof of convergence for leaky-Rayleigh networks as well. I think this is, like, if you want to, like, practice your understanding of the perceptron algorithm group, I think, like, generalizing it to leaky-Rayleigh networks is a nice exercise. And I guess an interesting question is, okay, why did I say leaky-Rayleigh? And, well, the answer is for Rayleigh, things become worse. That you can't actually prove convergence to a global minimum, because for Rayleigh networks, you have a bunch of critical points of gradient descent which aren't actually global minima. So you can have bad things that happen for Rayleigh networks. And another interesting question is, okay, so then what happens to this algorithm as alpha goes to 1? That's also a fun thing to think about. But maybe I'll leave it